Desmos does polar coordinates. Probably does. Does that? All right. So yesterday we talked that there's two topics in this section, right? Linear approximation and differentials. Linear approximation is basically like saying if you zoom in far enough on any given graph, like even this weird, it's interesting that I pulled that up there. Even this weird graph that we have on the screen here. If I zoom in far enough to any point, it looks less like the graph that was given and more linear every time I zoom in, right? So we can approximate any function by using a linear function and its derivative, right? And its derivative is going to give us the slope, and the point that we zoom in at is going to give us the coordinate that we can use for our linear approximation formula. Which again, the linear approximation formula is on the bottom of that chapter 3 cheat sheet that I gave you a while back. Okay, now, what is the difference between a linear approximation and a differential? Really, not much. The differential formula is dy is equal to f prime x dx. F prime x dx. And that, again, is straight from the point slope form of a line. Y minus y1 equals mx minus x1. If you think about the word differential, that the difference within that root word of differential just means subtraction, right? So if I'm finding the difference on y, that's y minus y1, that's the differential on y, is equal to f prime of x, which again, that's the slope, right? M is the slope there, is times the differential on x, which is x minus x1. All right, and then we studied this problem here, where we have not done example B yet, have we? I don't want to give it away. Let's do this. Don't look. Okay. All right. So what we're going to do is we're going to compare the values on true delta y and the differential on y, the dy. Now, what is the difference between the two? Remember, the delta y is the true difference in the y values. Is the true difference in the y values. And we looked yesterday, we said, well, if f of 2 is 9 and f of 2.05 is 9.717625, I know the difference, the true delta y between 2 and 2.05 is 0.717625, right? Subtract away. Okay, how do I find the differential then? And how does that apply to it? Well, the differential is dy is equal to f prime x dx. Well, what is f prime x? 3x squared plus 2x minus 2. So it's dy is equal to 3x squared plus 2x minus 2 dx. That is the differential equation. Dy is equal to f prime x dx. Then we plug in what we know. If we know, we can start at 2 here. Ooh, that's still an eraser. We can start at 2 here and say, well, if I want to start at 2 and find the differential away to 0.05, I know that dy is going to be equal to, well, I'm going to plug in f prime of 2 times the differential on x. Well, the differential on x between 2 and 2.05 is just 0.05. So I'm going to take f prime x times the differential on x. I'm going to take f prime of 2 times the differential from 2 to 2.05, which that's where we got the 0.7. Now, how close were we between true delta y and our differential on y? We were pretty close, right? We were pretty accurate. Within 17, almost 18 thousandths. That's pretty good, right? Now, we were comparing 2 and 2.05, right? What do you think is going to happen when I compare that to going from 2 to 2.01? What do you think is going to happen between true delta y and the differential of y, dy, when I instead of going from 2 to 2.05, I just go from 2 to 2.01. What do you think is going to happen between those two numbers? Do you have any guesses? Getting closer? Let's see. Okay, let's do example B now. Okay. And again, I am finding the x values of 2 and 2.01. Now, do I need to recalculate much? Well, when I'm finding the delta y is f of 2, which we know was 9, and f of 2.01, well, I just have to run that number. Let's plug that in. It's going to be something really close to 9, right? 2.01 cubed plus 2.01 squared minus 2 times 2.01. That's 201 up there. Look at that. That would have been bad. Would not have trusted my answer there. Insert a point. Okay, 2.01 cubed plus 2.01 squared minus 2 times 2.01 plus 1. 8.960701. 960701. 960701. 0.960701. So what is the true delta y? Well, delta y is equivalent to this value. Let me just minus 9, and we'll just say that it's positive. 0.39299. 0.039299. Yeah.
For the last 2.01, you just put 2.1.
Did I really? Did I seriously? Did I junk in the trunk. Hold on. Get out of there. There we go. Hold please. Thank you, Carlos. Plus 1. Okay, 9. Okay, change your numbers there. 9.140. I was wondering why it came up below. That was going to be weird. 140,701. 140,701. 140,701. 140. Oh, that's 9 points. Okay, that sounds a lot better. So my delta y is actually easier to find now. 0.140701. Right? That's my true delta y. Okay, now let's compare that to finding dy. Now, to find my differential equation, do I need to do anything different than I did above? No. The differential equation is just dy is equivalent to f prime, which was, again, 3x squared plus 2x minus 2. 3x squared minus 2x, plus 2x minus 2 dx. Whenever I ask you for a differential equation, that's what I'm asking you for right there. dy, difference in y, is equivalent to 3x squared plus 2x minus 2, the derivative. This technically should be in parentheses, times dx. Okay, let's plug in 2. The easier one to plug in. Now, when I go to plug in 2, aren't I going to get the exact same thing that I had? Right? This is still the same value. 3 times 4 is 12, plus 4 is 16, minus 2 is 14, right? 14 times dx. Well, what is the differential on x now? What's the differential between 2 and 2.01? 0.01. So that means I'm going to have 14 times 0.01. 0.14. How close are we now? Take a look here. Take a look here. Oh, sorry. There. Take a look there and there. How close are we now? We hypothesized correctly, right? We thought that it was going to get closer as we decrease our difference on x. The difference on y's are going to become closer and closer together. And that's actually true, right? So the closer and closer you make your x values, the similar delta y and dy actually become. Now, it's interesting to point out here. It's really interesting to point out. No matter what I would have chosen, right? No matter what I would have chosen, my differential equation would have stayed the same, right? The dy was always going to be 3x squared plus 2x minus 2 dx. Okay? And if you choose a given x value, that first part will never change. Like, if we wanted to compare 2 to anything else, we would always be plugging 2 in, therefore we would always be getting 14, right? dy would be equal to 14 dx. Right? So what we can do, and what that differential equations class that you may take sometime in the future does is it reduces your differential equation down to just a number times dx. So you can really think about, okay, based on where you're choosing your x value and how far away you want to get from that x value, you can figure out those simple equations like that, where you can say, well, what if I wanted to go to just between 2 and 2.001 now? We'll just multiply 14 by 0.001, multiply 14 by whatever differential you choose on x. And that's where things can get a little interesting. All right, last problem that we have. Don't tell me I gotta do this cold turkey. Oh, there we go. Phew. Okay, let's read the problem. Let's read it carefully. Oh, that's stats. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05. What is the maximum error in using this value of the radius to compute the volume of the sphere? Ooh, interesting here. The radius of a sphere, let's read it again. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of 0.05. What is the maximum error in using this value of the radius to compute the volume of the sphere? Now you got to really kind of understand what they're asking you here. You know your radius is 21, right? And I know my error is 0.05. I know my error is 0.05. Now, what truly is my error? Well, if I can say that I have a possible error of being 0.05, that means I can be 0.05 off of 21, right? 0.05 off of 21. So I could have 21 to 21.05, right? It could be the differential on x. The differential on my radius could be 0.05. So what I really am saying here is that dr is really 0.05. My differential on my radius is 0.05. I know I'm computing this with a possible error of 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? So what I'm really saying is, if I have a possibility of screwing up my radius by a factor of 0.05 centimeters, how much would that possibly change my volume? How much could that possibly change my volume? So what am I looking here? I'm looking for dV, right? What's the differential on my volume? How much is that truly going to change my volume? Well, we've got to come up with a differential equation where dV is going to be equal to really kind of like f prime x dr. I know this is bad notation here because I'm using x, but it's really f prime r dr, right? F prime. Now, what equation are we going to use? The volume formula, right? No, volume, radius of a sphere. Yeah, volume of a sphere. So volume formula of a sphere is V is equal to 4/3 pi r cubed, right? Yeah, pi r cubed. Because we know dr, we just have to compute really like f prime r. So let's find our derivative here. Okay, let's find our derivative here. Let's find the derivative of this piece. Bring down the 3. Now what happens when I bring down my 3? Yeah, that's going to cancel with my denominator, leaving us a 4 pi r squared. So there's my derivative of my equation, right? 4 pi r squared. So what I'm really saying here is that this is the differential on volume. dV is equal to 4 pi r squared dr. I took this f prime x, the derivative of the function that I have, plug it back in. 4 pi r squared is my new formula, which is crazy enough, the surface area of a sphere formula. And now I can plug that in. I can say, well, dV is going to be equal to, my differential on volume is going to be equal to 4 pi r squared. So my radius is 21. So 4 times pi times 21 squared times dr, which is 0.05. Let's see what that computes to be. 4 pi times 21 squared times 0.05. 277.1. We'll round it to 277.1. Volume, cubic centimeters. So what is that saying? That's saying that if I have a possible differential on x, a possible differential on my radius, a possible error of my radius is 0.05, then the possibility of my volume could err to be 277.1 centimeters cubed. Okay. So what we can now say is, well, if we want to make any decisions based on that, well, am I okay with that much error in my volume? Or do I need to go back and remeasure my radius or get more precise with the measurement of my radius so that my precision of my volume comes out to be a little bit better? Right? Am I okay with this much error in my volume? And if not, I need to get more precise with my radius. It's like, how precise do you need to be with the measurement of your radius? Well, it depends on the precision of your volume that you need to have. If you need to be more precise with your volume, you need to be way more precise with your radius. All right, that's it for that section. Let me stop the video.